Hello everyone, welcome to the lecture again. In the last lecture, we look at the work energy equation of a rigid body performing a plane motion. Today, we are going to look at the impulse momentum equation. So, we already know that for a particle, the impulse momentum equation is initial momentum P1 plus T1 to T2 f dt, which is the impulse equal to the final momentum. Now, we also know that the angular momentum of a rigid body is defined as the moment of linear momentum. Okay. So, it is denoted by either H or L. I will prefer L, that is equal to R cross P, where P is the linear momentum. Okay. Now, we also know that rate of change of angular momentum dl by dt, that is equal to moment or torque. Okay. So, this I can rewrite as summation m g, this is about the mass center, equal to L dot, okay, where dot represents the rate of change of that quantity. Okay. So, here this g represents mass center, okay, and also the angular momentum about the mass center is I bar omega, where I bar is the moment of inertia of the rigid body about the center of mass. Okay. Let us call this as equation number 1. Then similar to the impulse momentum equation for the particle, we have the impulse momentum equation for the rigid body, and it is given by L g initial plus T1 to T2 summation m g dt equal to L g 2. Okay. Here L g 1 is the initial angular momentum of the rigid body about the mass center. Integral T1 to T2 m g dt is the external angular impulse, and L g 2 is the final angular momentum again about g. Okay. So, this equation tells us that the initial angular momentum about the mass center g plus the external angular impulse about again g equals to the final angular momentum about g. Okay. Now, let us say we want to calculate the angular momentum of a rigid body about any point which may be or may not be on the rigid body. Okay. So, angular momentum about any point. Okay. So, let us say we have a rigid body and this rigid body has a linear velocity of v. So, therefore, let us say the momentum that is acting on the body is P equal to mv. Okay. And let us say this body is also rotating with an angular velocity omega. Therefore, the angular momentum about g will be Lg equal to I bar omega, where I bar is the moment of inertia of the rigid body about the mass center g. Okay. Let us say I want to calculate the angular momentum about a point O, which is at a distance of d from the line of action of P. Okay. Then the angular momentum about O will be the angular momentum about g plus the moment of momentum. The moment is mv and its momentum is, you have to multiply by the perpendicular distance, which is d. So, therefore, LO will be Lg is I bar omega plus mv d. So, you have to note that here this O may be a fixed point or a moving point, which may be on or off the body. Okay. So, this point may be on the body, as you have seen, or it may be off the body. Now, let us say this body rotates about a fixed point. So, if the body rotates about a fixed point. Okay. So, again we have this rigid body, let us fix some point on it. So, let us say this body is rotating about this fixed point. So, we have the linear momentum P equal to mv bar, and since this body is rotating with an angular velocity omega, therefore, this has a angular acceleration Lg equal to I bar omega, and let us say the perpendicular distance is r of the mass center g, and let us say this point is O. Okay. So, therefore, the angular momentum LO will be I bar omega, which is the angular momentum about the mass center g plus the moment of momentum. So, we have m v bar multiplied by the distance, which is r. Okay. Now, we know that because this is a fixed axis rotation, so therefore, v equal to r omega. So, therefore, LO will be I bar omega plus v is equal to r omega. So, we have m r r omega. So, m r square into omega, or omega is common. So, I can take I bar plus m r square into omega. Now, note that what is I bar plus m r square? I bar plus m r square is the moment of inertia of the rigid body about O. Okay. So, you can use the parallel axis theorem. Therefore, I can write down LO equal to IO into omega. Okay. And we have summation MO equal to LO dot. Therefore, the moment impulse equation becomes, for point O, it is the initial angular momentum about point O plus T1 to T2 summation MO dt, which is the external angular impulse, equal to LO2. So, this is the equation of impulse momentum about the point O. Okay. Now, based on this, let us look at some problems, and the first problem statement is following. The mass center G of the slender bar of mass 0.8 kg and length 0.4 meter is falling vertically with a velocity v equal to 2 meter per second at the instant depicted. Okay. Calculate the angular momentum L naught of the bar about point O if the angular velocity of the bar is 10 radian per second in the clockwise direction. Okay. So, we have this rod and it is falling with a velocity v equal to 2 meter per second, and it has a initial angular velocity omega equal to 10 radian per second. Its mass m is 0.8 kg and the length is 0.4 meter. Okay. And we have to calculate its angular momentum about point O. Okay. And point O is at a distance of 0.3 meter from the line of action of V. Okay. The angular momentum about O will be the angular momentum about G plus the moment of momentum, and the moment is mv and its moment is you have to multiply by the perpendicular distance, which is 0.3. Okay. Now, Lg will be I bar omega plus m is 0.8, velocity is 2 meter per second multiplied by 0.3. Now, I bar is the moment of inertia of the rod about its center of mass, and we know that it is m L square divided by 12 into omega plus 0.48. So, let us put the value. Mass is 0.8, length is 0.4 into 0.4 multiplied by 10, which is omega divided by 12 plus 0.48. So, this comes out to be 0.1067 plus 0.48, and this is equal to 0.587 kg meter square per second. Now, let us look at the another problem statement. Just after leaving the platform, the divers fully extended 80 kg body has a rotational speed of 0.3 revolution per second about an axis normal to the plane of the trajectory. Estimate the angular velocity omega later in the dive when the diver has assumed the tuck position. Okay. So, here we can assume that the diver's body as a uniform bar in the first case, and the sphere in the second case. Okay. So, for this assumption we can apply the conservation of angular momentum because no external angular impulse is applied. So, let us use the conservation of angular momentum. So, we have L g1 equal to L g2. So, Lg is the angular momentum and that is equal to I naught omega. So, we have in the first case m L square divided by 2, that is the moment of inertia, into omega 1 equal to 2 by 5 m r square into omega 2, okay, because L is equal to I omega. Okay. So, let us put the values. M will get cancelled because the mass is the same in both the cases. So, we have 1 by 12 into 2 into 2 and the omega 1 is 0.3 equal to 2 by 5 into r. R is the radius, the diameter is given, it is 0.7. So, therefore, the radius will be 0.7 divided by 2 into omega 2. Okay. And this gives omega 2 equal to 2.04 revolution per second. So, you can see that the omega has increased. Now, let us look at another problem statement. The 75 kg flywheel has a radius of gyration about its shaft axis of k equal to 0.50 meter and is subjected to the torque m equal to 10 into 1 minus e to the power minus t Newton meter, where t is in second. If the flywheel is at rest at time t equal to 0, determine its angular velocity omega at t equal to 3 second. So, again for this we can use the impulse momentum equation. So, we have Lg1 plus T1 to T2 summation mg dt equal to Lg2. Here it is given that initially the flywheel is at rest. So, therefore, Lg1 will be equal to 0. Now, Lg2 will be I bar omega, where I bar is the moment of inertia, and it is given that the radius of gyration is 0.5. Okay. So, therefore, I will be m k square. So, m is 75 kg into k is 0.50 square into omega. Okay. So, let us use equation number 1. So, therefore, we have integral 0 to 3 m is 10 into 1 minus e to the power minus t dt equal to 75 into 0.50 square into omega. This is using equation number 1. So, that gives you 10 into t plus e to the power minus t, and the limits are 0 to 3 equal to 75 into 0.5 square into omega, and that gives you omega equal to 1.093 radian per second. Now, let us look at one more question, and the problem statement is following. The force P which is applied to the cable wrapped around the central hub of the symmetrical wheel is increased slowly according to P equal to 6.5 t, where t is in second. After P is first applied, determine the angular velocity omega 2 of the wheel 10 second after P is applied, if the wheel is rolling to the left with a velocity of its center of 0.9 meter per second at time t equal to 0. It is given that the wheel which has a mass of 60 kg and a radius of gyration about its center of 250 mm, rolls without slipping. To solve this question, let us look at the impulse momentum diagram of the wheel. That is, what is the linear momentum, angular momentum, linear impulse and angular impulse which are acting on the wheel. So, initially we have this wheel which is moving with a linear momentum of m v1 and this wheel is also rotating. So, therefore, there will be a angular momentum which is equal to I bar omega 1. This is the situation at time t1 equal to 0. Then let us look at the linear and angular impulse which are acting on it. So, we have this wheel and this is the hub. Okay. So, first of all its weight is going to act. So, because of the weight the linear impulse will be integral mg which is f dt. Okay. And to balance this there will be a normal force. So, that will be integral n dt and we are applying a external force. So, therefore, the impulse will be p dt and also there will be a frictional forces, okay, the rolling resistance and that is equal to let us say f dt. Okay. And because of that we have the final situation. Okay. So, we have this hub, center of mass is g and this moves with a velocity of v2. So, therefore, linear momentum will be m v2 and it rolls with an angular velocity of omega 2. So, therefore, angular momentum will be I bar omega 2. This is the situation at t equal to 10 second. So, we can use both the linear impulse momentum equation and the angular impulse momentum equation. So, first let me apply the linear momentum equation which is p1 plus integral f dt from t1 to t2 equal to p2. Let me take this direction as positive. Now, all the parameters are given. For example, m is equal to 60 kg, v1 is equal to minus 0.9 meter per second, p equal to 6.5 t and v2 equal to r omega 2. Okay. So, let us put this over here. So, we have p equal to mv 60 into minus 0.9 plus 0 to 10 6.5 t minus f dt equal to 60 into 0.45 into omega 2. Let me call this equation number 1. Similarly, we have angular impulse momentum equation. Okay. So, that is Lg1 plus integral T1 to T2 summation mg dt equal to Lg2. Okay. Now, Lg1 is equal to I omega 1, okay, but its direction has changed. So, let us write down minus I omega 1, that is equal to minus m k square into omega 1, and omega is equal to V over R. Okay. So, therefore, this becomes minus m k square V 1 over R. Okay. And we can put the values. So, this comes out to be minus 60, 60 is the mass, k is 0.250, so 0.250 square into 0.9 divided by 0.450, and Lg2 will be I omega 2, that is equal to again m k square into omega 2, and again we have the values. So, m is 60, k is 0.250 square into omega 2. Now, for the rotation, let me take this direction as positive direction and put these values over here. So, we have Lg1 which is equal to minus 60 into 0.250 square into 0.9 over 0.450 plus integral mg dt. So, mg is the moment. So, that will be equal to integral 0 to 10. We have the force F which is acting at a distance of 0.450 meter. So, F into 0.450, this is the moment, minus we have force P which is acting at a distance of 0.225 meter. So, 6.5 T into 0.225 dt equal to Lg2. Okay. So, Lg2 is equal to 60 into 0.250 square into omega 2. Let us call this equation number 2. Now, we have equation number 1 and equation number 2, and this equation has two parameters and there are two equations. Therefore, from 1 and 2 we can find the value of omega 2, and omega 2 comes out to be 2.60 radian per second, which is in the clockwise direction. With this, let me stop here. See you in the next class. Thank you.